Okay, into our third subtopic for motion and relativity, and that is circular motion and gravitation. And in this first episode, we are just going to focus in on the circular motion stuff, and then we'll get into the gravitation stuff in some later episodes. Let's get into it. Okay, so what do we need to know about circular motion? An object moving in a circular path at a constant speed undergoes uniform circular motion. The object undergoes centripetal acceleration, which is directed towards the centre of the circle. So if we've got some object here moving around in a circle, the direction of the velocity is always at a tangent to the circle. So tangent is a line that just touches the circle. And the direction of the acceleration, and later on we're going to show why this is the direction of the acceleration, but just for now, the direction of the acceleration is towards the centre of the circle. And if the direction of the acceleration is towards the centre of the circle, then the direction of the force must be towards the centre of the circle, because basically Newton's second law says that a force will cause an acceleration in the direction of the force. Sounds a bit complicated, but hopefully you can see that that's just saying something fairly obvious. So the magnitude of the centripetal acceleration is constant for a given speed and radius, and is given by the formula A equals v squared on r. And in a couple of slides' time, we'll do some example problems with this formula. The formula v equals 2 pi r on t relates the speed to the period t for an object undergoing circular motion. I would hope everyone by now knows that the length of the circumference of a circle here of radius r, maybe I could label that on my diagram, radius r is 2 pi r. So 2 pi r represents the distance. Period is the time for one complete revolution. So velocity equals displacement or distance over time. 2 pi r is the distance. Period is the time. Again, what we'll do directly in a couple of slides' time is I'll go through an example where we solve problems using these types of formula. Actually, we're probably just going to focus in on that one. But this is, I think, fairly straightforward. It's not something that causes much challenge to people doing Year 12 physics. So finally, that what we need to know, and I'm going to talk about a couple other things as well, we need to use vector subtraction to show that the change in velocity, delta v, and hence the acceleration of an object over a very small time interval is directed towards the centre of the circular path. So I've shown that here, that it's directed towards the centre, the acceleration, and if the acceleration is the change in velocity, so if the change in velocity is towards the centre, then the acceleration must be towards the centre. So we'll do that over on this side of the circle. If we look at 2 points, and I'm just going to draw, so that point there, and then at another point here, and then this, let's say, is the initial. So we can draw a vector there representing the initial velocity. And then we can draw another vector here representing the final velocity. Now, delta v, so the change in velocity, is equal to vf minus vi. So if we come back here and we, probably know this by now, but we can also write that as delta v equals vf plus minus vi. And maybe I should be doing arrows here just to be really clear. We're talking about vector quantities. So if we add minus VI is same length but opposite in direction to oops, that's not quite right. I just want to get that line parallel but in opposite direction. So that's minus VI. So it's basically parallel to VI, but in the opposite direction. And we can see there that if we do the tip to tail rule, that vector there represents delta V. Therefore, that's the direction of the acceleration and therefore the direction of the force, and that's towards the center of the circle. So you need to be able to construct a diagram like what I've got there to show that. Just want to take a moment because sometimes this causes a little bit of confusion and talk about the difference between circular motion, which is what we're talking about here in this topic, and parabolic motion, which is what we were talking in the projectile motion topic. So in both cases, we have a constant force acting. But in the case of circular motion, the direction of the force is always changing, and the direction of the force is always perpendicular to the direction of motion. So as this spins around, the force is always perpendicular to motion. It's always changing direction. So direction is perpendicular to velocity. So basically what that means is that we have a case like this where we draw a circle and we've got, if you like, the velocity going around like that, and then we always have a force acting or an acceleration or a force. That one didn't draw that very well, sorry. Just trying to show that's at 90 degrees, back at 90 degrees. So that force, and therefore the acceleration, is always at 90 degrees, always perpendicular to the direction is always perpendicular to the velocity vector. So the direction of the force always changing. Sorry, not going what we're spelling here. The direction of the force always changing. So that's what leads to circular motion. In parabolic motion, like in projectile motion, the magnitude, or so the size, the magnitude and direction of force is constant. So what we've got there is if we've got a projectile going like that, we've got our velocity vectors going like that. The force, and therefore the acceleration, is always constant and always in the same direction. So that would be the force due to gravity in that case. So where the magnitude and the direction of the force is constant, we get parabolic motion. Where the magnitude of the force is constant, let's be more specific here, constant force in terms of magnitude. but the direction is changing because it's always perpendicular to velocity, then we get circular motion. Often comes up in questions to explain the difference between those two types of motion. So I just wanted to give you that clear picture in your head. Just also, we're going to go in more on this in the next slide. It talks here about the force. So what forces can cause this acceleration that leads to circular motion? Well, probably the easiest one to picture is the tension force, where we're spinning a ball or something on a string. So it's actually tension within that string that provides that force to basically keep the ball or whatever you're spinning in that circular motion, accelerating towards the centre in circular motion. The other example, and we'll explore this more later, or not in this video, but later in this topic, and that is gravity. Gravity is the force that gravity is the force that keeps satellites and planets and moons and all those sort of things moving in circular orbits as well. When we talk about cars, we talk about the frictional force between the tyres and the road, which is what provides the centripetal acceleration for a car to turn around a bend. But let's explore that more in the next slide. So before we explore that, I just want to briefly talk about the normal force. You may be familiar with this. If you are, that's great. If not, this is just a little an introduction. If you know about it, it's a recap. So the normal force is the reaction force that the ground or any surface pushes back up with in response to the force due to gravity, or what we often call the weight force. So we know from Newton's third law, for every action force, there's an equal and opposite reaction force. So gravity downwards is the action force. We get this normal force back up as the reaction force. Now, the normal force on an object is always perpendicular or at right angles to the surface the object is on, though. So in a horizontal case, that's pretty obvious, straight down, straight up. But where we have something sitting on a banked surface or sitting on an angle, that normal force will be perpendicular to the ground. So the gravitational force straight down, the normal force will be perpendicular to the ground. We'll talk about why that's important in a sec. So, just what do we need to know? On a flat curve, the friction force between the tyres and the road causes centripetal acceleration. So, we've got a car coming around a bend, it's on a flat road. Basically, normal weight force down due to gravity, normal force straight back up. But there is friction between the tyres and the road, and that friction is directed towards the centre of the circle, and that basically keeps the car moving in that circular motion. If you lose that friction, that's where your car will basically slide out and won't continue going in a circular motion. However, relying on friction can be a little bit fraught. Roads get wet, icy, things like that happen. So how can we improve the safety of a road? Well, if we bank the corner of a road, we now have force due to gravity straight downwards, normal force back up, but that's at perpendicular to the surface of the road. And you can see now this has a horizontal component, has both a vertical component and a horizontal component, and that's directed towards the centre of the circle. So because it's directed towards the centre of the circle, it's providing a centripetal acceleration. So you can create a situation where if this horizontal component of the normal force, so the normal force here in purple, if the horizontal component of that is significant enough, you don't need to rely on friction. That will provide all the force that's needed for an object to go around a corner. Sorry, that's my dog scratching. Now, we use that obviously on roads, so they'll often bank the corners on roads, but you'll also see that in places like I guess that's an example of a road, like in the American track racing where they race on banked tracks. You'd also see it in velodromes with cycling and that sort of thing. So what do you need to be able to do? You need to draw a diagram showing the force vectors and their components for a vehicle travelling on a flat curve and a bank curve. So here's our flat curve. Normal force equal and opposite to the gravitational force straight up. We need to rely on a frictional force to go around the corner. Here's the bank corner, and we show the horizontal component of the normal force is providing the force required for centripetal acceleration. Okay, let's keep moving. So just to finish up the circular motion part, let's just look. This is an old exam question. Hopefully when you look at this question, you go, oh, that's pretty simple. And it's typical of a number of the questions that you'll get in an exam. Not every question will be this simple, but a lot of the questions will be easy marks like this if you've thought about it. And I'm going to talk about a couple of other things just to, if you like, make this question a bit harder. The diagram shows a section of path of an object moving with uniform circular motion in a clockwise direction. On the diagram above, draw and label arrows at the point P to indicate the direction of the instantaneous velocity, v, of the object, and the instantaneous acceleration, a, of the object. So firstly, our velocity is always at a tangent. Make sure we label it. So there's our velocity vector. And secondly, I'm going to sort of have to guess the centre of the circle here is probably about there, I reckon. And it'll obviously be at perpendicular. That will be the direction of the acceleration. So, seems very simple, but does actually demonstrate good knowledge of those things we've been talking about that we've said that you need to know, the learning intention and the success criteria from the notes. Secondly, the object is travelling with a speed of 5 metres per second. The radius of the circular path is 12 metres. Calculate the magnitude of the instantaneous acceleration A of the object. So, the formula for acceleration for a circular object, and this is on your formula sheet, so you don't have to remember this as such, is A equals V squared on R. In the old days, you used to have to derive that formula, but we don't make you do that anymore. So, always substitute into your formula to show you understand what it's doing. So the velocity squared here is, or the velocity is 5 meters per second, and that's squared divided by 12, which is the radius, and that is going to be equal to, that's equal to 2.08 units for acceleration, are meters per second, but we only got two significant figures, so we're going to round that back to 2.1 meters per second, 2 sig figs, just to be sure. Now, a question like that, you weren't in this question, but a question like this, you could have also easily been, for example, maybe told the mass of that object, and then if you were told the mass of that object, you could easily have worked out the force that was required, and you could do that using, well, in 2 steps. You can go F equals mass times acceleration, and we've just worked out the acceleration there. Often, we do this quite a bit, so we'll just substitute the acceleration formula into that, which is V squared on R, and we'll go straight to F equals mv squared on R. If we get time, we'll actually play around with a prac in the lab where we use that formula as well. But yeah, that's, to me, it's a fairly straightforward calculation, and that's probably the only way you could have made that one slightly harder. So hopefully, yeah, that all seems pretty straightforward, pretty simple. I think that'll be it for this video, and then in the next video we will get into the gravitation stuff. Cheers. Make sure you hit like if you like this video, and click to subscribe if you want to see more of these videos. Cheers.